the water security issues we are facing and will face into the future. Thank
Okay.
you.
Okay, thanks, Bob and Censor, for the invitation. I'm honored. I would like something that probably my students hate most is a quiz. Okay, how many gallons per day do you think the average of us, one of us, uses? Gallon? How many gallons a day each one of us uses? A lot. Between 60 and 80. Okay? And actually, I was surprised that when the previous speaker talks about people using a handful of water to bathe every day, and how many gallons per day the average person in water-poor countries uses every day? 5. So in some people, you can be happy to use 5 gallons a day in many countries. So here on Oahu, the population is less than 1 million, and the Board of Water Supply pumps 150 million gallons every day. 150 million gallons a day. And also to maybe surprised to know that each time you open the faucet for 1 minute, that's 1 gallon. Okay? So 1 gallon of water each time you open the faucet for a minute. And of course, we have children, teenagers. We take a shower for how long? It would be nice for 10 minutes. Actually, some use 15 minutes, half an hour. So you can imagine that's like at least 30 gallons of water for a shower. Okay, and actually, I'm talking about regular faucets. Now, the power fountains, whatever, it's like up to 5 gallons a minute. Some of the shower heads, there are like 5 gallons a minute. So my main point now to take home is, each time you open the faucet, just think about 1 gallon, okay? So just, if you cut 1 gallon a day, right? How many for the whole island? A lot, right? If every one of us saves 1 gallon a day, that will be a lot. Okay, so I would like to talk today about the challenges that we have. I have it like 2 sections, one about knowledge and one about teaching. I start about knowledge. We live on an island, and we have a special characteristic for the island that includes geography, climate, hydrology, and scales. And of course, social and cultural issues. Hawaii, or small islands, are excellent laboratory because we talk about very small watersheds, and that takes this scale of time and space to be small. So if we compare between continental watersheds, we can see action in 5 years. Like climate change can show very quickly, much faster than it can show in continental places. That can make it interesting, but also very challenging, because the environment is harsh, and we cannot really access information easily because of that scale in space and time. Of course, also sustainability is challenging because we cannot really go and buy water from California. And of course, we have to live with what we got. Of course, surface water is important in Hawaii. Most of the water is used for these purposes, but basically it is only 50% of agriculture use. But if surface water is important, groundwater is very critical. We are talking about 100% almost of our domestic use. We talk about 50% of other uses comes from groundwater. And of course, we have limited resources. So we cannot really pump as much as we please. We have limits because of sustainability requirements. So because of different uses and limited resources, we have competing demands. And actually, you have plenty of rain. Think about it. This is billions of gallons of water every day. Like we talk about, places poor and 10 inches per year, and the wettest spot on Earth, 400 inches on Kauai. We should have plenty of water. However, the distribution is not perfect. Some areas don't have much. Waikiki have 10 to 20 inches, but the Ko'olau has 200, but people live in Waikiki. Yes, you. And of course, that creates huge conflicts. I can use also the Big Island as an example. The Hilo is very wet and the Kona is very dry. And that creates some conflict and demands. So that can create contested cases. And basically, if you do a small search, you can find many, many cases where the Water Commission holds hearings, try to find resolution when we have conflict of cases. Some of the cases still going on for years, like Waihuli ditch problem is still going on from the 90s or maybe before. Like when the sugar industry left the island, so there is some competition what to do with the water they left behind. Okay, so we have island special unique features such as geology and topography. And you can think about how difficult to do field work in an environment like this. And actually, many of the features are controlled here, like runoff or generation, things like that, where you have no idea about land use or land cover, obviously. Also, if you want to do drilling to find information about the ground system, you have to spend lots of money on drilling wells. So if you look at the geology, and we need this information to describe how water moves in the subsurface. And EQI is interested in the groundwater resources. So this is basically one of the biggest challenges. It tries to describe the geology of these areas. And depending on the exactly geographic location, we have very, very contrasting information. Could I have the light dimmed, please? The light dimmed. So you can see the green, the different colors here reflect different geologic formation. And the green here, low conductivity. When I talk about conductivity, I mean how easy or fast the water moves on the subsurface. So the green here reflects low conductivity material, and that's because of the dikes. So dikes has low conductivity and they stopped water from moving freely. So all the green here reflects specific materials of low conductivity. The same with the blue, but the blue here is much, much conductive, as we can see in the next one. Because a specific formation of geology here, this material is highly conductive. But that's not it. We have also, near the ocean, we have marine deposits and sediments that can even reflect different conductivities. This is like sediment, has low conductivity, but this is corals, which has much higher conductivity. Why I'm listing this? Because this is one of the challenges. This is subsurface. We cannot see it. It's very expensive to dig and try to find out. And because of variability, as you can see here, it's very difficult to describe this with great certainty. And even within the same formation, like remember from the previous screen, I'm sure you remember already, the basalt is high conductivity, but also it has different layering. So you can see this formation here is much higher conductivity than this one here. So to move between, even within the same formation, you have uncertainty about the exact conductivity. And of course, we can see this because it is a cut in the road or something, but you cannot really, above land or somewhere, you cannot easily find the information that you need. If we take a cross section through the island of Oahu, you can see the previous materials I talked about. So this is basically the basalt, which highly conductive. And this is the dike zone, which has less conductivity because of the dikes. And this is the sediment and the corals, which has variable conductivity, but they're actually less conductive on the average than basalt. So this basically nice to know, but this is very difficult, as I mentioned, because we don't know exactly the details of the subsurface. We know some of the surface features, but it is difficult to extend downward. And you could see here different ways to get the water. You have vertical wells, you have horizontal skimmer or something like that, that has advantage that you don't attract the salt water. By the way, you can see here the fresh water floating on the top of salt water, and there is some brackish zone in between. And if you use too much water, you shrink the fresh water and you get more salt water attracted in. And you can also expand the brackish zone. So in the old days, we had much thicker fresh water, but because of too much use, it is shrinking now. And this is simulation using some models for the water levels. You can see here the water level in the basalt up to maybe 6 meters above mean sea level. Meaning if you dig a well, the water would be measured at about 6 meters here, and it gets less and less as you come close to the ocean. This is where the dike zone is. And you can see the water is much higher, up to maybe 75 or 100 meters. And the Ko'olau and Waianae, you can see the high level water. So you can see big contrast of water levels. We know that water goes from Schofield to here and here, but we don't understand the mechanism. They call it Schofield Dam because it just confined water to higher level than here. Again, we talk about this because this complications and very difficult to really measure for certainty all the information that we need. So this is done by modeling, try to use available information to match with calculations. If they match, they should fall in this 45 degrees line, but you can see some uncertainties because of the lack of enough information. So to get this data or these simulations, we had to assume different conductivities. So if you've seen before, this is basalt, this is dike zone. So you can see here its conductivity is high, here is low, and you can see the range here. Almost non-conductive, up to 2,500 feet per day. This is very difficult to really describe accurately, and even it should not be uniform within the same formation, so it can still be variable. Okay, so additional difficulties or challenges here is climate. And we can see or expect to see a decrease in stream flows or rainfall. We can see wet areas gets wetter and dry area gets drier. We see extreme events for rain, sea level rise, and that can cause temperature increase and ocean acidification, and expected to have droughts, flooding, that's extreme events, and serious effects on ground recharge and water quality. And we already can see some changes because of climate change. And this work was done at the USGS. They found out decrease in stream flows. The stream carry now less water than they used to because of climate change and extreme or extended or using too much pumping. So streams are getting dry. Okay, so there is something called sustainability, which we can use the term to describe security in a sense. Because if there's not enough water, basically this is serious consequences. And we define sustainability as that you can use the water that you need without compromising the future needs. This is, there's different definitions for sustainability. This is one of them. And it's simply, you have limited resources, so we use it wisely for sake of the future uses. So then we have to do that by setting upper limit. Like say, if there is a system, groundwater system, we call it aquifer, by the way. This is a Latin word for the groundwater system. So each aquifer has to have a specific limit on how much used. And that should not be exceeded. So the local government that sets the limit, and you have to live within that. And that is called sustainable yield. And the trouble is the calculations are not accurate. They use simplified ways, and we know the numbers, but I will show you that actually is not very accurate indicators. So here is how it is calculated. So we assume that our aquifer is like a tank. Okay? Any of the aquifers is assumed to be like a tank. And you have water coming because of rain, we call it recharge, and water leaving to the ocean, we call it leakage. Then we have mixing here with ocean, so there is salt water, and transition, which is brackish water. So the more you draft, okay, this will create shrinking for the water level and mixing more with ocean, okay? So we try to create some balance here. If you draft too much, you will decrease the water level and affect the quality because of mixing. So water pumping is all lumped into one value. Like we have 15 wells, they all considered as one source of water. So if we know recharge, if we know leakage, if we know how much we want to control the water level and how much mixing, we can estimate the draft. Okay? So the draft is a sustainable yield. So based on these conditions here, we can control how much we can use from each aquifer. And here is the map. Okay? So for Burr Harbor here, I have the value about 165 million gallons a day. Okay, so this is a sustainable yield. Means all uses within this purple color area here should not exceed 165 million gallons a day. So if you wanna dig a well, you have to get a permit. Okay, the Water Commission will act and say yes or no if you are within this 165 million gallons a day. So you can see each aquifer has a number assigned to it. But these numbers, as I mentioned, are not very certain because they treat each one as a tank I showed you, which is not accurate because actually they connected to each other, right? So we are stealing from Honolulu or vice versa. So this is part of the uncertainty is we don't know really what happened at the boundaries between these. So these are management boundaries. They are not really physical boundaries. So this is one of the uncertainties about water in Hawaii. Okay, so because we use simplified approaches, we are not talking about site-specific areas. Each aquifer is the same, treated as the other. They are not similar, but each is treated as a tank, regardless of the actual condition on site. Then we don't consider any connection with surface water because surface water and groundwater are connected. You know, like surface water or streams are drained because you use too much groundwater, so we should include the connection. Also, we have no way of including social and ecological factors, like I am affecting the ocean if I use too much because the streams has less water, so not enough fresh water goes to the ocean. So I'm affecting the ecological environment. And social, like taro cultivation, is affected also by drying streams. So these things should be included in calculating the sustainable yield. Also, for the climate change, which is already upon us, we need to account for that. So the question now, we have these numbers, 165 to 90 for each specific aquifer. Are we really using sustainable practices? Let us check. So here is the numbers. These are the aquifers system or sectors on Oahu. Pearl Harbor is one of the most important one here, and there is a total of 6. And this number is different from 165, but I'm not sure which one is more accurate now. But so these are the sustainable yield of each one. And the total is 465 million gallons a day. But there is something actually, it's called permitted use, which is less. Okay? So the commission will even not go close to this one. It will try to stay within the permitted use. And the total permitted use is lower, right? 343. Great, right? We are within the sustainable yield. But actually, the actual use, as I mentioned, is 150 million gallons a day, which is what? Less than or close, less than the total, right? Even better, right? So we are not close to that. However, if you look at history, these are the water levels in this area in 1951. What are the ranges here? 24 feet, 25, 28, up to 30 feet, right? That's the water level above mean sea level, okay? If you dig a well, if you make a hole in the ground, the water would rise to this level, up to 30 feet. Okay. Then now this is in 2003. It is not exactly the same area, okay? But this one was here, but still give you some idea. What is the highest here? 20, right? Okay, that means how many feet we lost? Roughly 10, right? It was used to be up to 30 now. At that time, it is 20. So we lost like 10 feet of water level. If you have sustainable use, then we should not have that, right? Because that's exactly the tank I showed you. If you use wisely, you should not have any decline. So we are losing. But the bad news, even, it is worse than the 10 feet that I'm talking about, because this is the height I am talking about. Like if you have a well here, the water would rise 10 feet or 20 or whatever above the mean sea level. But if you look at the freshwater lens, roughly for every 1 foot here, I have 40 feet down. Okay? So if you lose 1 feet here, how many do you lose here? 40, right? Get the idea? The lens forms because of gravity, because fresh water depresses the salt water. So it is a good idea or beneficial to have lots of water above the mean sea level, because every 1 feet here translates to 40 there. So if you lose 10 feet here, you will be losing 10 plus 400. Okay, got the idea? So it is a huge loss. Okay. In addition, there is mixing between the two. The less the height, the more mixing, the more brackish that you have. And because of also increase in salinity, you can see the trends. So some of the wells, this is 1940 and 2000, so salinity is increasing in some wells. And that's like 250 is the limit, for water to be acceptable as for drinking. If it is higher than 250 is not good. So we are getting there unless we are careful. And I have this map. This is really unpublished. It is done by a student. It's not very accurate because he just used the values of salinity and the Board of Water Supply wells and drew this map. So just to give you some idea, you can see this red or yellow is there, because 250 is a number critical. So we are there. This is really bad. So we have to be careful about salinity issues. And this is water, the Board of Water Supply have this water use starting in 1970 up to 2006. You can see increasing trend. But it start to level off here. Maybe this is good news. From 1991, you can start leveling off. People use water more wisely. But if we continue with the original trend, it will be this way, which 1.6 million gallons a day per year increase. But if we are using wiser, maybe it's only 1 million gallon per day a year, which is still high, increasing, but we should plan for that. And now, not only we should be worried about water quantity, we should be worried about ecological factors, as I mentioned, and also as cultural. That includes, because basically there is water that ends up in the ocean, fresh water. So should we be worried about things carried by water, such as contaminant and sediment, and as well plan for cultural aspects like taro cultivation. So also, again, if water quantity is not enough, you have to have good water. So contamination is an issue. And because of land use activities, including recently use of pharmaceuticals and arsenic and nutrients, these are also can affect water wells or water in the wells. Also saltwater intrusion, as I mentioned. And there is also a critical issue about septic systems. There is more than 100,000 units in Hawaii because there is some areas are not connected to the sewer lines. And they release large amount, like 70 million gallons a day of minimally treated wastewater. And that can end up in the ocean and can increase nitrate in groundwater. And here is a map that we created for the density of septic systems, up to 500 units in a square mile. And this is the red areas. And you notice, of course, they are all shoreline. So bad news, they can contaminate the groundwater and the ocean, but also if you imagine sea level rise, then all the system will be underwater. That's really bad news. We have some arsenic contamination. This map is from the Big Island because of agriculture use of pesticides. And there is the brown are samples that exceed the 200 milligram per kilogram, which is a limit for contamination. As you can see, it exceeds that many places. The green is sugarcane areas. What we noticed, there is actually some values outside the agriculture area. And probably the only explanation is workers, after they finish during the day, whatever left over, maybe they dump it on the ground, for unwise decision. Fortunately, no arsenic has been found in water. Okay, so it's not a drinking water problem, but still, it can be in the future. Arsenic sticks to the soil hard, so it is hard to leave, but it can affect small children. Or when they play in the dirt, they can have in their nails, so it's not good to have it there. There is also pharmaceutical hormones and other organic wastewater contaminants. They found it in streams, they found it in groundwater. Fortunately, it's not affecting human directly because very small amounts. However, it can affect the ecological environment because they can affect fish, frogs, things like that, so they can create imbalance in the environment. So we have to worry about this as one of the difficult challenges in the future. Why is it difficult? Because there are too many, right? There is thousands and thousands of medical or the material that's used, and they are not required to look for them. So that can be a serious problem, to look for every medicine that we use. Also, we have to worry about the water, food, energy nexus, because there should be some coordination, because food, energy can generate water quality issues for water, and they consume water as well. So we have to consider multi-use of water in these activities. It looks like working in some places, like this is in Brazil, where the biodiesel is actually cheaper than the regular diesel. Okay, to go quickly now to EQI. So we need better approaches for estimating sustainability, and we need integrated approach that includes surface water and the groundwater interaction, water quality concerns, and social, economic, and ecological factors. Okay. And we try to address the challenges using sound scientific and policy level approaches, and to help the decision makers by providing the data and simulation or predictive capacity approaches. And we have planned to have a large, diverse workforce of researchers, including students, postdocs, and interact extensively with the community, includes government and other agencies. And very quickly, simulation models are a very important part of AQI or hydrology in general. And what's exactly models? There is different kind of models. There is something called conceptual model, which is our understanding of reality. Okay? The map I showed you earlier for Oahu, that's a conceptual model. This is our understanding of hydrology. But there is something called mathematical models, which I can take all this information and create some equations. Then when I solve this equation, it is called numerical model, which is basically a way to start making calculations. I can give you a quick model. It's like if I ask you how long it take you from Kaneohe to Honolulu, you say based on car speed and road condition or whatever, I take half an hour. That's the average. But if you want to be more accurate, you can include roadblocks, you can include repairs, you can include time of the day, you can include other drivers. So each one is a model. Okay? And each one is approximation of reality. And one is more accurate, but require more information. That's basically the whole thing in a nutshell. So this is basically a model, conceptual model of an aquifer. This is three-dimensional view. You can see here, this is the mountain side, this is the ocean side. And what we see here is the salinity distribution. The red is ocean salinity, salt, and the blue is fresh. And anything in between is less, is brackish here. So if I start the simulation, you can see the salt water is attracted by the wells, right? So here the well is getting salty. Okay, so that's a model that I can create to help me make the decision. Okay, why the ocean water is getting into the well? I'm using too much. Okay, let us change the practice and use less. So the models can be used to create scenarios. Okay, like climate change. See what will happen if climate changes. I can run scenario. I can add new wells or remove some or change land use. All of this just clicking, right? So the model helped me to do that. But how accurate the model is another issue. And I can maybe make it clearer by take cross sections in the same aquifer. This is where the two wells are located. So you can see now clearly how the salt water is attracted by the well. Okay? And the clock can give you the time, like saying how many years this thing will be happening. Okay? So models are very useful indeed, but as the classics say, garbage in, garbage out, right? So all the things I talked about earlier, the challenges, how to describe geology, how to know, basalt versus dike zones, what's the variability. This need to be identified as accurate as possible to give us good input to the simulation models. And this is a general scientific framework that we'll use in EKY. So we start by simple but realistic model, okay? Maybe one that has water levels and salinity effects. Then start using the actual data that we have now and run the models and make some use of this data and use it directly for decision making by integrated social sciences, okay? What is in social sciences is like economics, is like ecological factor, things like that. Then make decisions that help the managers to decide on some acts, like say, decide on the sustainable yield, new values for sustainable yield. And create also visualization for the people to access through computers to find the data that they need. So this is, we call it phase one. Okay, but as I mentioned, the models are not accurate. So we need some improvement. Then we can collect data, new data. That is what our teams are doing, to collect new data here and integrate it with all the models, try to make them better. Okay, try to make them better. And to go interactive way, like collect data and improve models. Then see what models, what data they need, then guide the field collection. And we call it phase two. Then pick up the best representative model and start making calculations here. So you can see both this track one and the track two end up in the same way. But when one of them supposedly more accurate by collecting new data. Maybe it will not be, okay? But at least you utilize the best science to see what's really the difference between track one and the track two. And I will show you quickly what the type of field studies we planned, but they are mainly related to geophysical, submarine, groundwater discharge. This is water going through the ocean, microbial, geochemical, and sensor. These are the field data that being collected to use with the models. Very quickly, I don't think I need to go all through that. It just geophysical work will be, it is like taking X-ray for the subsurface, okay? That's the simplest way to say it, because it's expensive to dig wells, but geophysical can send a signal and receive it and give you some idea about in the subsurface. There is submarine ground discharge. This is water leaving the aquifer to the ocean. So we have techniques to measure how much water is leaving the ocean, and this is an important part of the conceptual model. Okay, we need to know how much water goes to the ocean. Microbial is by looking at the composition, the diversity, and density. We can see if two aquifers are connected. Okay, if they share the same information about bacteria, we can know if they are connected to each other. We can also see bacteria as water quality indicator. Okay. There is a sensor. This is some equipment to put inside the well, okay? And it can measure a few things like water level, like pressure, like temperature, salinity. This information can be used in the models. Then geochemistry can be used to correlate chemicals to land use and find out travel times. If I can find certain chemical here and check it there, I can find out the travel time and I can find out where is it coming from. Is it agriculture or septic or whatever? That's also important for the models. Then here is everything will go into social science. Basically, if we have a budget, like everything goes in and goes out, we can use economics and social factors to guide the decision-making process. Here is very quickly examples of modeling. This is like a whole island of Oahu salinity profile using the computer simulation to give you the distribution of salinity. Purple here is fresh, red is salty, and anything in between. And the model can give you a slice like this to see what is inside. This kind of very detailed still need to be worked out, but it gives us an idea about the capabilities of the software. We can do also cross-section, very high resolution of salinity. This is like the ocean here, and this is the land. So it gives you the freshwater lens and the brackish zone and the salt. And it can show you the flow pattern and the velocities of water as it exits from the aquifer here. So to calibrate, we need to validate, to compare all of these numbers against what we have in reality, which is the data collected in the field. And this is maybe example of the final product. We know chemicals will follow this path to the ocean and end up in certain wells. So we can find out, like the travel times. We can find out how we can reduce water quality if we know where is the water coming from. So that could be helpful in the decision-making process. Okay, so that was the first part. How am I doing on time? Okay, any quick questions here? Yes?
Yeah, I think like Long Island, are you looking at any injection wells like of gray water, maybe treated gray water, where you can, below well sites to keep that salt water bowls from coming up to the...
Yeah, actually, this is a very sensitive issue here. I don't think it is allowed. But they allow recycle, they allow reuse for golf courses. That's used. And actually, we have certain issues with injected treated water, like the wastewater is either disposed of in the ocean after treatment or injected in the brackish zone. And we found out there is direct connection between the injection point and the ocean. And there is a court case in Maui, they are looking into that. But I don't think deep injection is for recycled water is allowed. They consider this for the area next to the ocean. Remember what we call the sedimentary coral? They thought about doing that. Not because it is like allowed for as a drinking source. It's just to create more pressure to stop the ocean water from escaping. Right, that's what you're talking about. But this is not for drinking area, it's not allowed to do.
Right, no, but just to keep the saltwater bowls from coming in.
Right. Okay.
So you showed us that the water usage plateaued, but was that correlated with a decline in agriculture?
This is actually the drinking water. No, so it's mostly, I think, by being people more careful. Yes?
How much do you see increase in leakage and saltwater intrusion from coastal development factors, such as when you build a hotel, you put the pillars inside the ground, like through the capstone? Do we see more freshwater leakage or loss of fresh water from that? And likewise with building a harbor, dredging a harbor, where you cut into the capstone, do you see increased leakage in saltwater?
Right. I'm not sure about the first one, but I'm sure about marinas. They build marinas, and that's terrible because they break this. By the way, it's called the caprock. That's where that sediment is. So when you create marina, you break that caprock. Actually, they call it the caprock because that's what it does, right? Capping the fresh water. So you need to get environmental impact statement, but it is a very bad idea to do. By the way, we are lucky to have this in Oahu and the older islands. But the big island and younger island, they don't have the caprock, so you have too much fresh water escape. Yes?
I just can address part of your question in the first part. The Muilili Karst, I was just in there last week. In the 1920s, when they were driving the pilings into the karst, it ruptured the system, and for several months, about 1 billion gallons of water drained out of the system and created sinkholes all through Muilili down here. I'll have some video of that tomorrow inside the system. But yeah, it did it did affect the system. Sorry to.
No, perfect. All right. Okay. Any other quick questions?
Can you briefly speak to desalination discussions or?
Yeah, I believe it's still expensive. But this, we might stuck with it in the future. And this is actually part of our project. They will work on the, like which years desalination would be required. Okay, so, but that should be in the future for sure. I think the price now is maybe 4 times as more expensive as well water.
So
Yes.
that's any good news.
No, I think I drink the faucet water. Is that good enough? I don't buy bottled water. So I actually trust the Department of Health and the Board of Water Supply. I believe the water coming to my house is okay. I drink it. Do you know how much is the water that we pay for? How much do we pay here? Anyone? Yes. They sell it by 1,000 gallons. How much is 1,000 gallons? $6. $6. They want to increase it to maybe 8 or 10 or whatever in the future. How much you buy a gallon of water in the supermarket? This is for 1,000 gallons. Yes.
Doesn't the cost of the water depend on what kind of user you are?
Yes, they have like a structure, and they have I guess how much also water they use.
So the more water you use, the cheaper it is.
No.
The more you use, the more expensive
Yes.
per unit.
Right. So you pay more if you use more water.
Okay.
Right.
You pay more if you're connected to the sewer versus on a septic.
Right. And actually, if you live in most of area here, you get one invoice for water and sewer. And sewer is more expensive than the water. They take a ratio, just a ratio, depending on how much water you use. I use in my area, we pay fixed amount for the two. So. By the way, I mentioned that we use 150 million gallons a day here. Do you know how much wastewater we generate? How much wastewater we generate? 100 million gallons a day. Can you imagine? Can you imagine if we use them somehow rather than being wastewater? It is water wasted, right?
Is that included in our agricultural foods that we eat? Is that included in the agricultural foods that we eat? Or is that used for water?
No, I think that's the Board of Water Supply. It's not for irrigation. That's drinking.
Because when we eat a corn or whatever, that
Yeah.
takes a hell of a lot of water.
Right, but I don't think it is included in the 100. I cannot check.
So it's even higher.
Yeah. Yes, ma'am.
I was wondering about, we saw fountains that were running here on the island when we were driving around yesterday. So is that fresh water? Is that gray water? Is that?
I hope they are not fresh water. I hope they recycle the water with the ocean. And actually, sorry?
Most fountains recycle the water.
Right.
They don't waste it.
Right, but still you have evaporation, some evaporation there. And they have this
Salt
in,
water, or is it, that's what we would hope.
yeah, I hope it should be there. And actually in Las Vegas, they have this water show.
Yeah.
It's horrible. It's evaporation, it's bad, it's recycle. But of course, you know that Nevada, they get like 4 inches a year or something
Yeah, where are they getting that water?
from the ground. Yes.
How does the change in forest cover affect recharge?
Yes. And maybe if you'd like to add a few words to that.
Oh, well, forests have the highest infiltration rate of any land cover because of all the macropores and micropores that the roots create around. Depending on the type of forest, you may see differences in how much water actually is infiltrated versus transpired back to the atmosphere, right? Some trees use more water than others, in particular due to the extensive deforestation that had occurred following post-European contact and fires and cattle and sheep and goats, and a lot of the koalau being denuded of forest cover. Foresters in the 1930s planted fast-growing trees that could grow on degraded soils in order to try and restore the watershed, but in some cases, these trees also trees are pumped. They pump a lot of water back to the atmosphere, so the type of forest cover could make a difference. My own work was comparing native forest to forest invaded by strawberry guava. And the common perception is that invasive species use more water. Unfortunately, my results were a little less conclusive. I found that at about a threshold of about 50% strawberry guava cover, that we started to see an increase in transpiration, and so a reduction in water that made it back into the ground. But it was highly dependent on the age of the trees and the size, relative native and invaded. So it's a complicated process. But yeah, forests, in my opinion, from what I know, will increase. Forests will increase infiltration into the ground, but forests are also pumps. So forests are returning water back to the atmosphere. But in general, they're going to slow down the flow of water and allow more of it to get into the ground. And you're going to see higher base flows in the streams with the forest there. So when in times of ecological drought, perhaps, where you have lower stream flow, it will be higher if you have a forest there than if you don't.
Is there a way you can measure
Okay.
the trend over time, how much water is recharging, or is it are we getting as much recharge or less moving into the future?
I don't think I heard you well.
I just wonder if there's ways to measure the efficiency of the forest to recharge aquifers.
Yes, there is actually, there is on campus here, there is a group doing that. They have tower, they can measure it, maybe not directly, but you can measure meteorological information and relate it to the water budget and estimate how much recharge goes in. And you can measure also the soil water content and calibrate. Okay, so talking about teaching challenges, Bob said teaching is, yes, sure. So talk about how teaching a hydrogeology class can be challenging. And basically, in my class, I have to deal with students from different units, geology and geophysics, civil engineering, tropical ag, global environmental science. I allow, of course, this is like 400 level, so I allow graduate and undergraduate in the class. And people hate math. So once they see equations, they completely turn it off. So I need to deal with that. I actually remove the prereq, so I teach that, and I think they enjoy it a little more by saying, yeah, I know what's dH by dy means now. Okay, I also like to keep the content up to date because this is very important and related to everyday life. And I would like to eliminate exam failures. I allow them to bring a cheat sheet, one cheat sheet. I give them the equations they need, but more equations than they need. We do some, practice exams, stuff like that, but still some don't enjoy it. And also hoping to attract more students with all of these problems. So this is my geology and geophysics class. So what I do is mix theory with lab experiments, field trips, computer simulations, and active case studies, and movies. Synchronization is difficult because theory has to match the lab. The field trips can be random sometimes, so it takes some effort to do well. Here is some pictures from the lab. So this is some of the equipment they use. Help, for a student to understand the theory. And they usually enjoy the field trips. And here is some facilities on the island. This is like a lava shaft. This is underwater exploration or development. And here is Wahi'i waterfalls. This is also outside a water development facility. And this is again outside the facility, and this is inside. So this is like they collect water from the dike zone. So it's very clean, fresh water, perfect water there. Then this is Nuano Reservoir. This like observation tower. This is you have the gate here, and we have a project now to capture this water in the reservoir and inject it in the ground. This is like one way to conserve water. We visit the Manoa landslide. I can show them, last year it was like this year it was like this, and probably a few $100,000 or something in between. And the student can see actual failures and houses disappearing and moved. Then also I cover cases. This is like Del Monte site here in Oahu. This is like contamination because of pesticides, spillage. And it started in the 1977, the case. So this is, I call it Superfund site. So the government is taking over, but Del Monte is paying for the cost. And here is a quick history. It started 77, and now it's still going on. Okay? I don't think you need to read all of that, just to tell you how terrible these things are. And we have hundreds or thousands of sites like this countrywide.
What was the spill?
It was,
What spilled?
it was I think, what is it called, herbicide.
Okay.
They had like 500 gallons spilled when they were uploading or putting in from the tank to the trucks. And unfortunately, or maybe I don't know if I call it fortunately, okay, so they started doing the work, but they found extra additional contamination. It turns out this thing was leaking many years before. Okay, so it was just like a trigger of the old practices as well. And this is what example of, like, I can use this forever, right? I say, I want to update my class. Yes, here is the update. This is going on. There is also this case I cover in Massachusetts, and they have similar conditions. And this one, they made a movie out of it, so I show the movie in my class. This is a civil action. The real life is better than the book. There is a book, and the book is better than the movie. But John Travolta is good. This is also a very nice movie that you can enjoy. This is a case in California also. Okay. Here is a cheat sheet of one of the students. This is 8.5 by 11. He copied all my slides. Okay, just I think he spent a huge time, and this is not my wishes. I tell them, take notes, not copy, because this will be way to study. Don't bring the cheat sheet to study in the class, right? But he wanted to study. I think he got C with generosity. Okay, so I usually make slides from the class for field trips and show it at the end. I try to make it a little bit interesting or funny. Probably they will take it and tell the other student to come to take the class or something. So these are at the beginning of the class. You can see happy, smiling faces. Then I say, oh, guys, how about the final? And this is what you get. Okay, so I think I am doing well in terms of this one, this one, this one. I still need to work on this one. Okay, thank you very much.
Thank you very much.
You're welcome.
So, I'm standing between you and lunch. And I recognize that, but I have a couple of announcements. Greg Chung is here from Akiwai. Greg is